Okay, now I would like to explain about Fourier series. Fourier series applied to a periodic signal, so I would like to explain the periodic signal first. Periodic signal is defined like this way. For all time t, this equation should be satisfied. Okay, if there is a t0 that satisfies these conditions, then this t0 is called the fundamental period. This one is called the period. Okay, inverse of the period is called the fundamental frequency. That's this one. So this is period, and this is fundamental frequency. And the angular frequency is defined by 2 pi times omega 0. This is called angular frequency. Angular frequency has a unit of radian per second. Frequency has a unit hertz. In fact, hertz means that 1 over sec. You can see T0 is a sec unit. So I talk about what is a period and fundamental frequency and angular frequency. Now the last one is harmonic frequency. Harmonic frequency is k times omega 0. This is called harmonic frequency, and k taking positive and negative integer number. So k times omega 0. K times omega 0 is called harmonic frequencies. So you need to know that the terms, what is the fundamental frequency and what is harmonic frequency says. The second one, series expansion. I would like to explain about that. If a signal expressed by the linear combination of complex exponential function. Complex exponential is a sinusoidal function. In that case, the complex exponential has a harmonic frequency. So linear combination of any harmonic signals is a periodic with a fundamental period. It means that xt is a sum of any harmonic signal component. Then it satisfies these conditions for all t. Any given t. The reason is this one. Omega 0 times t0 equals to 2 pi. It's obvious from these relationships. 2 pi is a period of complex exponential function. E to the j 2 pi always 1. This is 1. So any k multiples of that is 1 to the k. That's the same as 1. So if xt can be expressed in the sum of harmonic signals, then signal is periodic. Inversely, if periodic signal exists, then any periodic signal can be expressed by the linear combination of harmonically related complex exponential signals. So this is Fourier series. So if signal is periodic, then that signal can be expressed by the sum of harmonically related complex exponential sum. Okay, this is the Fourier series. But the precondition that the Fourier series exists is Dirichlet conditions. Dirichlet condition are this one. The first requirement is absolutely integrable. That's this requirement. Over one period, absolute xt taking the integration should be finite. That's the first condition. The second conditions, for any given bound interval, the maximum and minimum, up and down, it means that the maximum value and minimum value should be finite. Here shows a counter example. It means that xt satisfy the first conditions. Okay, by taking the absolute value, the magnitude is maximum is 1. So by taking integration over the period, the absolute value is less than 2 pi. Okay, equal or less than. Okay, anyway, this is finite, it's okay. It satisfies the first condition. But the second condition does not satisfy. It means that t goes to 0, its signal is very fast, so an infinite number of maxima and minima exist around the t equals 0. So it doesn't satisfy the second one. The last one, in any finite interval of time, there should be a finite number of discontinuity should be exist. So this condition is a little peculiar, but look at here. This one is defined every 8, 16 like this. So period is absolutely 8. Period is 8. This is defined like this way. Half of the time is 1. The another half of time, this is 4. Then this is 10. This is 1.5. And another half of this one is half. Another half of this one, half. If approaching to the 8, there are infinite number of discontinuity exist that violate the third conditions. So these three conditions should be satisfied that Fourier series exist. But the violation of the delete conditions is quite unusual. So in practical situations, it doesn't happen. So we don't care about that one. Usual signal satisfy these three conditions. Okay. Now we would like to investigate a little bit deeper. Okay, here is a periodic signal xt. But it's a real signal. So we assume that the xt is periodic and the value is a real signal. Then xt can be, you know that any periodic signal can be expressed by the complex exponential. It's a harmonic complex exponential sum. So that's the Fourier series definition. Look at here, xt. If xt is periodic, then xt can be expressed by the linear combination of harmonic components. Linear combination of harmonic components are this one. So xt can be expressed by the linear combination of harmonic component. So we assume that xt is periodic, so it can be expressed by the linear combination of harmonic components. Okay, but another requirement is that xt is a real number. Then we just changing the k with minus k. Then c minus k and e to the minus j k omega 0. It's the same thing. So xt can be expressed without changing like that. But you can see it by taking the conjugate of this one. By taking conjugate of xt should be xt because it's a real number. So by taking the conjugate of this one, we'll give this expression. By comparing these two things, this is also xt because it's a real number. We're taking the conjugate of this one. But real number doesn't affect it by the conjugate. So these two equations should be equal. By comparing, these two values should be equal. So if xt is a periodic and real signal, then k to the conjugate is c minus k. It means that the c minus k index equals the coefficient of c minus k's harmonic component should be equals to the k's harmonic component to the conjugate. Usually ck is complex number. Okay. Look at here that the xt is equals to ck times e to the j omega k omega 0 t. Then in case of k equals to 0, that is the c 0, and k equals to 0, then exponential term is equals to 1. So only c0 coefficient exists here, and we changing the k 1 to the infinity, then is a positive coefficient here, and the minus infinity to the minus 1 is shown here. K goes to 1 to the infinity, then it goes to minus 1 to the minus infinity. We know that this complex conjugate sum, you know that this one is a positive index, and this one is complex conjugate term. Okay, c minus k is ck conjugate. So some of these, some of the complex conjugate will give the real terms. The complex terms will disappear by these summations. So it can be expressed to two times real value of ck e to the j omega 0t. And ck is complex number. Let's assume that ck is ak plus jbk. At this moment, the k means the harmony index. K changing 1 to the infinity, it's an integer number. If we represent the complex number ck as a real part is ak, imaginary part is jbk, then it can be expressed like that. By taking product, you know what, e to the j k omega 0 are cosine k omega 0t plus j sine k omega 0t. So ak times cosine is a real number and bk times sine gives a minus real number. So we have to taking the real value of this one. So that real number comes from the product between ak and cosine and jbk times j sine. Those two terms are real number. The other ones are complex number. It means that pk times cosine or ak times sine is complex number, so it's a dropout. So it can be expressed in this way. So ak times cosine and bk times sine. So this is Fourier series coefficient. So if we started from the periodic signal xt with real number cases. In that cases, kth coefficient should satisfy the complex conjugate conditions like this one, and by use of that one we derive the Fourier series expression in case of real signals. Fourier series expansion for a real valued periodic signal can be expressed like this way. At here, ck times e to the j k omega 0 t, this one is the harmonic signal component, and the ck usually complex number, and in case of real number, ck c minus k is the ck conjugate. If it's satisfied, we can express the ak with small capital like that way, and c0 a0, and b minus bk, okay, 2 times ak. This one is ak minus 2 times bk are bk, and a and b are real number. We assume that the complex number decomposed like this way. So a and b are real numbers. So this one is a cosine and sine Fourier series expression. This one is a complex Fourier series expression. Okay. Now we would like to find out the coefficient of ck or akbk. So to find out that one, we need to refer to functional dot product as we studied in previous lecture. So here shows that e to the jn omega 0 t times e to the minus jm omega t. This one is m times harmonic, so n times harmonic, and taking integration over period. Okay, dt changing from one period. Then it looks like this one. At here, if n equals m, then this becomes the unit. In that case, taking integration over one period, it gives the t0 value. If n is not equal to 0, then sinusoidal signal integrated over the whole period, it should be 0. It means if dot product of these two functions is 0, means independent or orthogonal. So this means that orthogonal set. So function is orthogonal if n is not equal to m. So this is one of the property of complex exponential function. If n equals to m, it has a t0 value, but if not, it's a 0. It's independent each other. So what about cosine and sine with nmm? So in these cases, by taking integrations, you know what the cosine sine equations looks like this one. Anyway, it is integer multiple of omega 0. So by taking, okay, dt is omitted here. By taking integration over the whole period, sine or, you know, the sinusoidal function should be 0. So in any cases, sine and cosine are independent. It's orthogonal. Cosine times cosine cases, If n and m are equal cases, it becomes t over 2 if n equals to m. But n is not equal to m, it is orthogonal. It's the same for the sine. Sine n omega t, sine m omega 0 t are orthogonal if m is not equal to n, but m equals to n. The cosine or sine square will give the t0 over 2. Okay, so this proves that the dot product between the sinusoidal functions. Okay, by use of those property, we can derive the how to find out the coefficient. Okay, try on this one. We know that the xt can be expressed by some linear combination of harmonic component. The harmonic component is this one, k times omega 0 t. So if xt is a periodic, it satisfies these conditions. So we would like to figure out this coefficient. So to find out that one, we take a dot product between xt with e to the minus j n omega 0 t. We make a dot product over a period. Then we replaced xt with a linear combination of harmonic component. Then that integration given like this way. So if k is not equal to n, it's 0. If k equals to n, then ck times t0, cn times, you know that it has only non-zero value when k equals to n. Okay, then ck becomes the cn, and this goes to the 1, so taking integration over t0 will give a t0 value. So cn can be expressed 1 over t0 times dot product between xt and exponential minus jn omega 0 t. So in the complex coefficient are given like this one. So cn is complex number. So cn can be expressed the magnitude and angle like that. And DC component means that the n equals to 0. That is the DC component. If taking n equals to 0, means that this n equals to 0, then this goes to the 0. Then the equation will be given like that. So this is the DC component. And okay, now we know that how to figure out the complex coefficient of Cn in case of these expressions. What about the cosine was sine series expansion? I mean that if xn, xt is expressed a0 plus some k times ak cosine k omega 0 t plus some k bk sine sine k omega 0 okay, kth harmonic component. If we expand xt in these patterns, then we can do the same things to find out ak or bk. Xt is dot producted with cosine omega t. Okay. Then we can replace xt with this one. You know that if n is not 0, then a0 times cosine is 0. We know that a0 already. If sine is producted over here, it goes to 0. It doesn't affecting. If ak times cosine k omega 0, then it means that ak times cosine k times omega 0 t and the sum over k. Only these parts are remained. But by taking integration the whole period, only non-zero value exists when k are equals to n. Okay, that's the shown here. Only k equals to n, it has value. So if you consider that one, it will give only k equals to n. That means an. Integral t0 times cosine square dt. This will give t0 over 2. Okay, like that. So this gives the an expression. An 2 over t0 integral t0 xt cosine and omega 0 t over dt. So this is the an equations. Similarly, bn can be found by taking these integrations. xt sine and omega 0 t. Okay, this will give bn coefficient. So what we have done, Fourier series are applied to a periodic signal. And if signal is a period, it has a fundamental frequency and harmonic frequency are related by the integer multiple of fundamental frequency. If signal is a periodic, then that signal can be expressed by linear combination of harmonic component, like these equations. Then we consider the real signal, real periodic signal. In that cases, we can, using this relationship, from this result, we can figure out the negative index number is complex conjugate of the corresponding index. So by use of this property, we can derive the cosine sine expression. We can express xt with a complex exponential like this one, or we can express as a real number expression like this one. So both is possible. This one is a complex exponential equation, but this one is a real sine or cosine sum. It's the same case if signal is real. And to find out the coefficient, we refer to the functional dot product. Taking the dot product complex exponential give like this result. In case of n equals to m, in that case only has a non-zero value. All the other cases is 0. Cosine and sine always orthogonal, regardless of n conditions. Regardless of them, it is orthogonal. Cosine dot cosine or sine dot sine has only non-zero value when n equals n. On these conditions, all the other cases is 0. That's the orthogonal property. Due to that orthogonal property, we can figure out the coefficient by use of the dot product between the signal and the basis function. This is called basis function. At this time, basis is a complex exponential. Then we can find out complex coefficient. What about the cosine and sine case? It's the same. The signal is take a dot product with cosine basis functions. This is basis functions. Then we can figure out the an coefficient. And by taking the sine dot product with a basis function is this one, then we can find out the bn coefficient like that. And then lastly, I already talked about the Dirichlet conditions, convergence of Fourier series or existence of Fourier series. The first condition is absolutely integrable. The second one, finite number of maxima and minima. This shows that the counterexample, it doesn't satisfy these conditions. The last one is that in any finite interval of time, there are only finite number of discontinuities should be existed. These three says that the Dirichlet condition, but most of the function satisfy these conditions. So you don't need to care about that one. Okay.